Let's try to apply the tool of the Fourier transform over an ordinary differential equation. Okay, so this is an ordinary differential equation. The second derivative negative, the second derivative of x plus 25 y of x equal to delta Dirac of x. What is this delta Dirac? This is just a fancy way to say that this function takes a value of 0 in any x. So here the independent variable is x. So here it doesn't matter what x do you have, it has a value of 0, except at point 0. At point 0 you have a value of infinite or something extremely large. And the rest, it continues to go to have a value of 0. Okay? This equation could be representing, I don't know, a circuit in electronics or a mechanical system. If it is a circuit in electronics, probably this delta Dirac means that you actually connect the voltage over the a very high voltage over the circuit in a short period of time. Or if it is a mechanical system, it means that you are actually applying an impulse. So sometimes the name of this function is also called impulsing function or delta Dirac function. In your mind, you only need to think that this function have a value of 0 all the time, infinitely large at 0, and 0 the rest of the variable x, in this case not time, x for us. Okay, so don't worry too much about this delta Dirac function. It's just another function, similar like sine of x, cosine of x. It has a graph, it has a derivative, it has everything. Okay, so let's try apply the Laplace transform over this differential equation, over this ordinary differential equation. So we apply the Laplace transform in the left and in the right side of the equation. Because the Laplace transform is a linear operator, I can do this. I can actually extract this negative sign and then Fourier transform of the second derivative of y of x plus 25 or Laplace transform, Fourier transform. I think I said Laplace transform. Okay, Fourier transform of y of x. This is equal to Fourier transform. I'm using this red color just to show you where I am applying the Fourier transform of the delta Dirac of x. Okay, let's use a table of the Fourier transform. I will provide the table in the description of this video. So the table I have here, a table for the Fourier transforms. For instance, the Fourier transform of the second derivative. Where can I find that? Let me increase the size of this. Second derivative, here it is. The second derivative is IW squared Fourier transform of f. So here is going to be minus IW squared the Fourier transform of y. I can use this symbol. I can express this as a capital letter. We know that it's going to be in the frequency domain. I am just following the instructions in the table, plus 25 this y of w. Remember that this is what we are looking for. We need to find y. And the Fourier transform of the impulse, let me see, the impulse, here you have the Fourier transform of the delta Dirac, or the impulse is just 1. So this is 1. So we can certainly isolate y. Let's see. Here remember that I means square root of minus 1. If you power to the power 2, it's going to be minus 1. With this minus 1, it's just going to be plus 1. So this is w squared y of w plus 25 y of w. Y is what we are looking for. So I can isolate y. This is equal to 1 over w squared plus 25. Okay. So I was looking for y. I already find y. What's the problem? That I find it in the frequency domain. I don't want it in the frequency domain. I want it in the x domain in this case. So let's try to apply the inverse Fourier transform. Let's look for a function with this shape in the frequency domain to see what is the function in the x domain. Here this table uses t instead of x. Okay, whenever we see t, we put x. Here you have a rule that have the same shape. You can see 2a over a squared plus w squared. Yeah, it's the same. In our case, a is going to be 5. So in the numerator, I need 10. So I need a 10 here. Let's put it. If I put 10 there, I can put 10 in the denominator. If I simplify, it's going to be the same. Okay? So I am ready. Let me use another color. So y in the x domain is going to be equal to 1 over 10, because the inverse Fourier transform is also a linear operator, so the constants just go out. And what is the inverse Fourier transform of this function? Is just e to the power minus I absolute value of t, in our case x. So e to the power minus 5 absolute value of x. Okay. So we were able to find one solution for this differential equation. Actually, the solution that we found is the non-homogeneous solution of this equation. This solution is not the non-homogeneous solution of this equation. If somebody wants to plot this solution, you know, the plot of this solution is, for instance, if x is a positive value, the absolute value just keep the same. It's going to be an exponential, a negative exponential function. So it's going to have this shape. So this point is going to be 1 over 10. While in the negative, if x is negative, the absolute value just turns into positive. So it's going to have the same value as in the positive case. So the shape is something like this. This is the shape of this function. The moment that we apply this rule that the Fourier transform of the second derivative is iy squared times y in the frequency domain, we assume that our function y actually converge to 0 in positive and negative, which is something that you can see here. Our function converges to 0 in the minus infinite and also in the plus infinite. So it looks good. It looks good that we apply that rule. So let's find this time the homogeneous solution for this equation. So in order to find the homogeneous solution of this equation, I only need to equal to 0 and solve that differential equation. So let's use another color. So I am going to find the solution of the equation second derivative of y plus 25 of y of x is equal to 0. This is the homogeneous equation. So I will find the homogeneous solution and then I will join with this non-homogeneous solution and I will find the total solution. So how do we solve this second order homogeneous differential equation? It's very easy. You can find the characteristic equation of this solution just by looking at the equation. Is just minus r squared plus 25 equals 0. It means that you can find the two roots of this characteristic equation. This is called the characteristic equation of this differential equation. You can easily see that the two roots are plus and minus 5. So this is the case of the two real roots. So it's very easy for you to find the solution, the homogeneous solution. We can use an H here to show that is a homogeneous solution. Here we can just put no NH, which is non-homogeneous solution. This homogeneous solution is just the e to the power 5x. So this is the first solution, the first root, linear combined with the second root, which is e to the power minus 5x. Okay? So the total solution, the final total solution, drums here. The final solution is just joining the homogeneous plus the non-homogeneous. So the total solution is going to be y of x going to be equal to c1 e to the power 5x plus c2 e to the power minus 5x plus 1 over 10 e to the power minus 5 absolute value of x. Okay? So this is the total solution. Why the Fourier transform tool just find this non-homogeneous solution? Because it's the only one that accepts a Fourier transform. The Fourier transform, in order to apply the Fourier transform, you need a function that is absolutely integrated from minus infinite to plus infinite, which is true for this part of the solution, because if you see the graph, it looks like this. So you can integrate from minus infinite to plus infinite, which is not true for the other parts of the solutions. For instance, this one, the graph is something like this. You cannot integrate this from minus infinite to plus infinite because it not converges to a value. Similar for the for the second solution. The second solution, this part is if you grab this function, is something like this. So you cannot integrate from minus infinite to plus infinite because it doesn't converge. Okay? So with the tool of the Fourier transform, you will be able to find only this non-homogeneous solution. But it's going to be very easy to find the homogeneous one. Thank you.